Absolute zero is the lowest possible temperature that can theoretically be achieved, corresponding to 0 Kelvin (K), or approximately minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit. At absolute zero, the particles that make up matter, such as atoms or molecules, have their minimum possible energy. This is also the point at which all molecular motion ceases. According to the laws of thermodynamics, it is not possible to reach absolute zero through any finite number of processes. The third law of thermodynamics, known as the Nernst heat theorem, states that it is impossible to reach absolute zero through a finite number of operations. This law implies that no process can cool an object to absolute zero in a finite number of steps. There are a few reasons why reaching absolute zero is impossible. The cooling process itself requires energy. Cooling involves the removal of energy from a system. As a substance cools, it releases heat energy, and to further cool it down, that released heat energy needs to be removed. As the temperature approaches absolute zero, it becomes increasingly difficult to remove the remaining energy. The uncertainty principle. According to the Heisenberg uncertainty principle in quantum mechanics, there is a fundamental limit to the precision with which we can measure certain pairs of physical properties. This principle implies that at absolute zero, particles would have precisely known positions and zero momentum, violating the uncertainty principle. This contradiction suggests that reaching absolute zero is not physically achievable. Quantum mechanical effects. At extremely low temperatures, quantum mechanical effects become significant. Particles, such as atoms, exhibit behaviors like bose-einstein condensation and superfluidity, which prevent them from reaching absolute zero. These quantum effects impose limitations on how cold a system can become. While scientists have come close to achieving extremely low temperatures, such as a few billionths of a Kelvin, absolute zero remains an unattainable goal due to the principles of thermodynamics and quantum mechanics. However, studying systems at very low temperatures has led to fascinating discoveries and advances in fields such as condensed matter physics and quantum computing.